Second speaker this morning is Nikolay Nikolov from Oxford. The title of the talk is Homology torsion growth of higher rank lattices.
Thank you. It's a pleasure to be here. It's a great place to do mathematics. So I thank the organizers for inviting me. Today I will start with discussion of approximations of groups, because this workshop has approximations in its title. So what do we mean by an approximation of a group? Well, I'll tell you what it means for me. So let gamma be finitely generated and residually finite. Finite group. So we want somehow finite approximations to that group. So what is the obvious thing we can do? We can take a collection of finite index subgroups. And the obvious thing we can do is we can insist that they have trivial intersections, and we can assume that they are normal, and we can assume that they're ordered. Yeah. Right? And so that will, and then the quotients that we get, so the finite quotients will in all for all purposes will capture our group gamma will embed there. Yeah. But we can relax these conditions. So you've seen already talks about Sophic approximations, which are more general things. So a more general setup is to consider, let me just erase this now. This will be a special case. Yeah, in the box. This will be a special case. So let's consider something called Farber sequences. So this is called a Farber sequence. If the following things happen, if I take for any non-identity element in gamma, if I take the fixed points, the number of fixed points of G acting on the coset space gamma mod gamma I, and I divide by the index, then this sequence of numbers, as it goes over the sequence of groups gamma I, this tends to 0. Okay. Another way to say this is that the sequence of permutation representations that we get gamma acting on the coset spaces gamma mod gamma I is a sequence of Sophic approximations for my group. In the, yeah. Okay. And another way, let me just rephrase it in the language of measure preserving actions, is to say that gamma acts almost everywhere freely on the profinite space gamma mod gamma I. This is if the gamma I are ordered by inclusions. Is a chain. So if they are ordered by inclusion, then we can form the inverse limit of the finite spaces of the finite coset spaces. This is a profinite space with a countable with a counting measure, which induces a probability measure on the profinite space, and the action of gamma acting by by multiplication on the left on the space is almost everywhere free. So, okay. And another topic of my talk is lattices. So now let's take what do we mean now? Approximation of Lie groups. So let G be, in my talk will be, I will restrict to the case when G is a simple Lie group. And most of the time I assume that usually, if I forget in some theorems, I'm assuming to have trivial center. But for this definition, you don't really need it. And now let we have gamma I be a sequence of lattices in G. Let X be the symmetric space, G modulo the compact maximal compact subgroup, and we want to say in some way that if I take the collection of let Mi be the orbifold lambda I when I factor lambda the action of the quotient of the symmetric space by the action of lambda I. So this is an orbifold, but it's also a space with a finite with a finite volume, because this is a sequence of lattices. And I want to say that in definition, so the sequence gamma I is Farber, or if you prefer, you can say it's a Benjamini-Schramm sequence. Okay. If what happens, well, what we want to say that somehow we want to be able to say that somehow these spaces model the symmetric space. Yeah. And what is one way to say it is that for any positive, think of it as a big real number R, if I look at the Artin part of my orbifold, so I take the ith space, and we look at the collection of elements in it in which the injectivity radius is less than R. So in other words, if I look at the ball of radius R, this is not isometric. This does not lift bijectively to the R ball in the symmetric space. Yeah, this is the Artin part. I look at the volume of the Artin part. I divide by the volume of the whole space Mi, and I want this to tend to 0 as I tends to infinity. Okay. Okay, so this is a in some sense it's the Sophic approximation version of for graphs that is here. So the Benjamini-Schramm started this Benjamini-Schramm convergence for graph means exactly this thing for graphs. Yeah. And for graphs, if you here consider the Schreier graphs on the coset spaces, this is exactly the same concept. That's why I call it Farber, just because it's easier to say Farber rather than Benjamini-Schramm. Okay. So here's a non-trivial result that we proved. Here's a theorem. This is a proof, a theorem with 7 authors. So I'll just write the initials: Miklos Abert, Nicolas Bergeron, Ian Beringer, Tzachi Gelander, myself, Jean Rembourg, and Ido Samet. But so here's what the theorem says: that if R is if the real rank of G is at least 2, this is commonly referred as the case of a Lie group, simple Lie group of higher rank, and the center is trivial. Just again, the center is trivial. Then any sequence lambda I with increasing covolume, so the volume of these guys mi tending to infinity, is actually Farba. Right, so you get, this is a quite spectacular result on the face. You just take any sequence of lattices, and then the quotient, the orbifolds approximate the space. Yeah. Okay, so this involves certain. I mean, this relies on several steps, and one of the key steps I should mention is actually quite deep. This is the Stuck-Zimmer theorem. Yep. Which says that any probability transitive ergodic any ergodic probability measure preserving action of such a lattice is basically coming if such a Lie group of this form is actually coming from almost surely the stabilizer of a point is a lattice. And we also use some we developed this theory of invariant random subgroups where we reduce it to this theorem, and we use property T as well. But I just want to illustrate the example of an approximation, yeah, that automatically happens. This is not the case at all in rank 1, yeah, obviously, because in rank 1, the moment you have a normal subgroup of infinite index in a lattice, you can such that the quotient is reasonably finite. You can actually just take your lattices to be finite index subgroups in a given lattice, but with a non-trivial intersection. Right. Okay. Okay. So when we have approximations, then we study a classical case is the study the growth of some invariants, and in particular, the most natural invariants in the case of manifolds. These are their Betti numbers. So in the case of a group, this is the nth Betti number of a group. This is the dimension of the n homology group with coefficients in Q over Q. And in order to define it, you need that the group is of type Fn. You need that the group has some finite dimensional resolution up to degree n. Let's assume it's defined. Yeah. Okay. In particular, beta 1 is always defined if gamma is finitely generated. Okay. And then here is a theorem. We have to look. So Luke proved this theorem in the case of in this situation when you have gamma is of type Fn plus 1. So, for example, e.g. finitely presented if n is 1. So, you choose your integer n, yeah, at the beginning, and you take a finitely generated residually finite group of type Fn plus 1 and take such a Farba sequence. If this is a Farba sequence, then actually if you look at the nth Betti number of gamma I and you divide by the index of gamma I in gamma, this always tends to a limit which is beta script beta to gamma. This is the nth L2 Betti number of gamma. Yeah. So the normalized Betti numbers converge, and moreover they converge to something which it does not depend on the choice of the sequence, just depends on the group. So I don't have time to define these L2 Betti numbers here, but you can take this as a definition in this case. Yeah. No, this is just for discrete. This is for discrete groups. Yes, I'm going to now go to the lattices in a second. And he proved it for chains, normal chains with trivial intersection, and then Farber generalized it to Farber chains with his condition. Yeah, right. Now, what happens here? Can we do something similar? And the answer is yes. So now, suppose now let's another theorem again of these 7 people. Is now suppose that now G is a Lie group. Now assume that this is a Farber sequence of lattices. In G. And also assume we need this condition that we cannot avoid, which we call uniformly discrete. Okay. Now, the uniformly discrete condition says that there is some epsilon such that the injectivity radius of each these quotient manifolds is at least epsilon. So exists, I'll just state it here, exists some epsilon bigger than 0 such that mi less epsilon is actually the empty set. Okay. Right. Now this, in the case of arithmetic manifolds in higher rank Lie groups, every lattice in the higher rank Lie group is arithmetic, and in that case, this is known as a Margulis conjecture. There's a common bound on the injectivity radius of arithmetic manifolds. Yeah. But let's assuming this, then we have the same conclusion. If I look at the Betti number of mi, and I divide by the volume of mi, then this converges to the L2 Betti number of the symmetric space. Okay, which actually is very simple thing. It's almost always 0, so it's 0 unless n is not equal to the half of the dimension of x. And here is basically the Euler characteristic of x. Okay, the Euler characteristic of the compact duo. So it's something to do with the Euler characteristic here. Something. Easy. So in the middle dimension, it's something easy to compute. It's the Euler characteristic of the compact duo of x divided by the volume of the compact duo of x. Yeah. Right. Now, and in many cases, so it's easier. For example, for groups like SLN, as long as n is bigger than 2, it's always 0. Okay. Now, this generalizes a theorem, a classic theorem of de George and Waller. So here, say George and Waller. Which prove the same result in the case when you take a sequence of normal finite index subgroups with trivial intersection in one cocompact lattice in my Lie group. Okay. In this case, if you're going to take a sequence of finite index subgroups in a given cocompact lattice, then this is automatic because this epsilon will be the injectivity radius of the original lattice. So any cover of it will have bigger injectivity radius, so you never you're never going to contradict this. Yeah. Okay, so this is something classically studied from the 1980s, and then there are kind of various generalizations to the multiplicities of unitary representations of these lattices, and there's quite a lot of theory about it. Okay. No, here this is true in general. But in case if rank is bigger than 2, then this first condition is automatic, and uniformly discrete is expected by the Margulis conjecture. But we can't say anything about the Margulis conjecture. So in my talk, so this is just as an introduction to approximations and why they give you interesting results. So now I want to talk about different invariants. So this was about the Betti numbers. Okay. Let's do other more difficult invariants. Somehow for Betti numbers the situation is quite satisfactory. We have these theorems, but we always want to know more. So let's try these. There are two invariants that I'm going to talk about. The first one is the minimal number, the rank of the group D of G is the minimal size of a generating set. Gamma, and of course this is trivially a bound on the first Betti number. Yeah, that's clear. And the other invariant I'm going to talk is the torsion, the size of the torsion group in the. Let's restrict just to the first homology group. So this is just the abelianization. So if we abelianize gamma, if you abelianize gamma, then you get a finitely generated abelian group, and we take the torsion subgroup, the size of the torsion subgroup. Okay. Now, I mean, many of you have seen versions of this talk before, so I'll just quickly mention that when studying the growth of the number of generators, just as the growth of the Betti numbers, you see that they can grow at most linearly. Yeah. So the natural thing to study is for number of generators is to study the rate of linear growth. So define something which is called the rank gradient of gamma with respect to the so here I'm assuming that gamma I is a chain. In order to define it in this nice way, if I assume that the set of subgroups are ordered by inclusion, then I can just take the limit of the number of generators divided by the index, and I subtract 1 for monotonicity purposes. To be sure that this limit exists, is the best way to show it is to notice that this is a monotonically decreasing sequence, because the number of generators cannot grow more than linearly in terms of the number of relations from the Nielsen-Schreier bound. So this is a monotonically decreasing sequence. Okay. What about torsion? This grows at most linearly. Now it's easy to see that when the group is finitely presented, so the torsion, let me just give it a name actually. Let's call this guy T of gamma. Okay, T for torsion in abelianization. And then easy to see that if gamma is finitely presented, then T of gamma I grows at most exponentially. So there's some constant, exists some C, which really depends only on the group. such that the torsion of any finite index subgroup is at most C to the index of the subgroup. Yeah. Yes, this is an easy lemma to do with presentations and linear algebra. So it makes sense to study. So here then for study the behavior of, we take log of the torsion of gamma I and divide by the index of gamma I. Okay, study this sequence. No, but now I cannot say that this is a monotonic sequence. There is nothing really, there's no really obvious any obvious properties of this sequence of rational numbers. So I cannot even claim that the limit exists in general. But maybe I can study the lim sup or the lim inf of this sequence. Okay. So here's a result that we'll be able to prove. Now, rank gradient has been studied first by a topologist, by Mark Lackenby. He was the one who defined it, and he used it to study the properties of hyperbolic three manifolds. So there's by now quite a lot of literature on the growth of the number of generators. Well, here's one result that actually was known before. So this is a definition: right-angled groups. A group gamma is right-angled. This is not the same as a right-angled arching group. Just a name that suggests connection is that if gamma is generated by elements, several elements, finitely many, which are of infinite order and sequentially commuting, yeah, and Gi commutes with Gi plus 1 for all I 1, 2, and minus 1. So each one commutes with the previous one. Yeah. Okay. And of course, there are many examples. Groups of infinite center, group in which you have one central element of infinite order. It will be such a group because you can connect every second element will be this central element. Or examples more in the spirit of this talk. If you take the unimodular group for n bigger than 2, then you can order the unipotent subgroups in a way that they commute sequentially. Yeah. Many solvable groups, certainly, yeah. Okay, nilpotent groups, of course. Now, this class of groups was defined actually by Gaboureau. Was studied by Gaboureau and Damien Gaboureau, and he proved a theorem about them. He proved that if gamma is rank right-angled, then gamma has fixed price 1. Okay, this is a notion from ergodic theory. If you have a measure preserving ergodic action of gamma on a probability space, then this action has always cost equal to 1. Okay, and I won't have time to tell you what cost is, but it is in some way say a measure of how we can generate the equivalence relation of the defined by the orbit, by the orbits of gamma. Okay.
What's a fixed price?
Hmm?
You can have a fixed price for 1. That's the last one.
Yes. So this means that the cost of gamma acting on every probability space measure. So this, if this is a probability, a measurable space of total measure 1, a non-atomic on which gamma acts ergodically by measure preserving transformations, then the cost of this action is equal to 1. Yes. This is a notion defined by Levitt and studied extensively by Gabourot, and it's in some way it's a way to it measures how difficult it is to generate the equivalence relation of the orbits of gamma on omega. I don't have time. I won't have time to define it. But I will relate it to rank gradient. So here is a theorem that I proved with Miklos Abert. So we proved that actually, if gamma I is a Farber chain, assuming that we have Farber chains, then actually this rank gradient of gamma acting on gamma I on the rank gradient of this thing here, is actually exactly equal to the cost of gamma acting on omega minus 1, where omega is this inverse limit, this inverse limit of these profinite spaces. Yeah. So this, as I said earlier, this is just basically this is just you can think of it as a tree. This is the boundary of the coset tree, where you take the sequence of cosets, each one refines the other, you get a tree, and the sequence of paths, the set of paths is the boundary, that's the probability space. And the group gamma acts on this boundary, and there's a relationship between the cost, which I haven't defined, but with this limit, which I have defined. Gamma is right angled. Sorry. Yes. Oh, no, wait. No, here no. Here no. This is in general. Wait. No, this is in general. But now if you put together with right angled, you immediately get that so as a corollary, of course we get that for right angled groups, the rank gradient is always 0 for any Farber chain. Yeah? So corollary. If gamma is right angled, then the rank gradient with respect to any chain, and this is Farber chain, then this limit is 0. Our proof really needs that it's a chain, actually, because we really need that this is a probability. We really need this object, and there's no easy way to define this thing if it's not a chain. So we really need it to chain, and then of course what we can ask: do we really need it as a chain? Maybe it's true in general. Yes. So here I should say an open question is whether this limit depends on the choice of the chain. If you take a different chain, say normal subgroups with trivial intersection, you can ask, do you get always the same limit? And it's an open question, which is still embarrassingly open. Probably the biggest open question in this field. Okay. All right. Okay. What about torsion? So torsion growth is harder to study than Betti numbers, and in some ways just as hard as rank gradient. And the reason is that if you look how it's defined, if you have a finely presented group, then you can easily present the abelianization. But then you're talking about the torsion of presentation of an abelian group, which is basically expressed as the greatest common divisor of certain determinants of some minors in the matrix presenting a group. So it's very difficult to get lower bound for the torsion, and it's much easier to get upper bounds for the torsion. In particular, for amenable groups, for finely presented groups, finely presented amenable groups, this torsion always grows sub-exponentially. This was the first thing I proved with Aditi K and Peter Kropholler. But we wanted to know something about lattices, and this talk is about lattices, so I'll talk about right-angled groups again. So now let's try right-angled groups. So this is now a theorem with Abert, Gelander, and myself. Okay. So now let gamma be right-angled again. And gamma I any Farber sequence so now it's allowed that you take your finite index subgroups all over the place, not necessarily ordered by inclusion, but they have to be Farber. They have to approximate the group. Then, well, as we suspected, the rank gradient from that sequence, of course, I define it only for chains, but for sequence, you can just take just the same definition, and then the statement also says that the limit exists. So here the growth is sublinear of the number of subgroups, but more then even more interestingly, you get that the torsion is sub-exponential. The ratio of log of the torsion and stabilization divided by the index also tends to 0. Okay, so the proof of this is partially inspired by the result by Damian Gabourov, where he proves that these groups have fixed price. So we basically take his proof and make it quantitative, and also we make it finite. So we work the way the proof works. We work in the Schreier graphs of gamma mod gamma I, and we find a nice way to remove many of the edges of the Schreier graph, which still keep the graphs connected, but they don't distort the metric very much. So I don't have time to say too much about the proof. But essentially, it's a graph theoretic argument inspired by Gabourov and Gabor-Elek as well. And at some stage, it just boils down to estimates of this sort. Whenever you have a presentation of a amenable group, of an abelian group with relations of bounded length, and suppose you can control the length of the relations in some way, then you also have a bound on the size of the abelianization from essentially linear algebra arguments from determinants. Okay, I don't have time to go into the detail, but this is old stuff. I mean, I have already talked about this. And for lattices, we wanted to apply this to lattices. Of course, some lattices are right-angled, and for there we do get also results for sequences of subgroups in these lattices. The ones that I wrote here, this right-angled one this is a non-cocompact lattice. So it's highly non-obvious that are there right-angled cocompact lattices. So we found some. So another theorem from that paper is that the groups that we considered, SLN R n bigger than 2 and SO n2 and at least 9 have right-angled cocompact lattices. Okay. So at least we have one lattice, one cocompact lattice there, and where if we take a Farber sequence of subgroups of finite index, we will get sublinear growth of rank and sub-exponential growth of torsion. So previously we didn't know if there is even one example of a cocompact sequence with this property. So now we know an example. But we're really motivated by this conjecture that I want to write down. Let's be very ambitious here and make a conjecture. So far I just talked about working rank gradient and torsion growth in one group, but let's be bold and let's consider sequence of lattices in a high rank Lie group. Conjecture. Okay, so let lambda I be a sequence of lattices in high rank G with increasing with volume tending to infinity, with the volume of these guys mi tending to infinity. By the way, it's sufficient to assume that in this case, by theorem of Wang, that simply you're not repeating them up to conjugacy, because there's a theorem of Wang that says that there are only finitely many lattices of given co-volume in a high rank Lie group. Okay, this will come up again. The conjecture is, of course, we expect that the number of generators divided by the co-volume is 0, and the torsion grows up exponentially. Log torsion grows up exponentially. Okay. So this is a very difficult conjecture, especially in the case of cocompact lattices. We only know it for certain cocompact lattices, for certain right-angled cocompact lambda 1, and then taking a sequence inside lambda 1. This is basically the only thing we know in the cocompact case. But I wanted to say today that talking with talking with a graduate student from Israel called Mark Schusterman. I should write his name, yes, that's nice. Schusterman. Okay, and we made the following observation. Okay, so the observation is the following. Well, let me state the sequence of observation. Well, the assumption is, of course, we're now going to assume that each lambda i's are not cocompact. Each is not cocompact. Yeah. Then, okay, what does it mean? This means that because so by the in high rank Lie group, all the lattices are arithmetic, and not cocompact lattices means that they have unipotent elements. They have their rational rank is positive, so they have unipotent elements, and then it's known by result of many people that each lambda I has the congruence subgroup property. This is work by I believe Pinchuk, Raghunathan, and really it builds on work by many people. Okay, so this is for rank, will help. For torsion, what really helps is the fact that the Abelianization is finite. Yeah, H1 of lambda z is finite. This is because of Kazhdan property T. Yeah, you have property T, so every Abelianization of such a lattice is finite. Okay, but this means that it's relatively easy to control torsion in Abelianization if it's already finite, because then it behaves well under finite index subgroups. It's really just estimating sizes, which otherwise, if this was not finite, then it's really a problem to estimate torsion if you pass to a finite index subgroup. Okay. There's another very key result here, a result by Sharma and Venkataramana, which says that the number of generators of a lattice here of non-uniform is at most the number of generators of the profinite completion plus 3. Okay. No, it even says more.
Yes, yes.
But we need something more. We need that. I didn't state this properly. So the statement there says that. No, actually, yeah, this is exactly what we need. Yes, yes. But now you see the profinite completion is practically the same as the congruence completion because the lattice has a congruent subgroup property. So if you know that, then you understand the number of generators. Now you understand very well the congruence completion of so-called principal congruent subgroups. Not every arithmetic lattice is principal, but there's this work by Misha Beulipetsky and Alex Lubotsky, where they study lattice growth of of these in G, yeah, especially for in particular for non-uniform, for non-cocompact. Yeah. So basically, the structure of this lambda is very well understood. Yeah, the structure of lambda is well controlled by certain principal arithmetic, by certain principal congruent subgroups. So it's not true that each lambda is a principal congruent subgroup, but it's not very far away from a principal congruent subgroup. So if you put everything together, our observation is these all results are pretty deep and hard. But the observation itself is putting them together, and it says then the conjecture is true. For non-cocompact sequence. Right. So okay. So it looks nice. We just did half of the conjecture with no work at all. For the experts, though, it's everybody knows that it feels that the cocompact lattices are the hard bit. So that's where the real work will be. In particular, even the congruent subgroup properties is wide open for cocompact lattices in SLNR. So we don't know it. Okay. So I started after.
At least for the right-hand side of the conjecture, it's only the congruent subgroup.
Yes. Yes. Okay. I wanted to say something. I'll just spend another 5 minutes. I didn't say anything about rank 1, and maybe rank 1 is the most interesting case. So let me just say something about rank 1. Where I learned about the growth of torsion is these conjectures of Bergeron and Venkatesh. So they make a sequence of very precise conjecture about the growth of torsion, but let's specialize this to the case where the lambda is arithmetic lattice in PSL2C, and we take lambda I principal congruent subgroups inside gamma, yeah. Inside delta. Then the conjecture in this case is that this torsion grows exactly exponentially with a very precise expectation for the exponent. If I take the log of the torsion and liberalization, divide by the index, and take the limit, I will get here basically the co-volume of the original lattice rescaled by a certain number which depends on the choice of the volume form, but in the standard case, in the standard choice, you get some multiple of pi. Okay, so notice that there's one way to read this is the following. So the torsion in the urbanization you can see from the finite images of your lattice. So this is something that is completely determined by the profinite completion of the lattice. This formula says that if it's true, it says that the co-volume is determined by the profinite completion. Yeah. So there's a lot of work by Martin Brightson, Henry Wilton, Alan Reed on profinite completions of Kleinian groups. So this is small, something small and related. And finally, now this is a very specific choice of lattices, right? Congruence lattices, and these are not in general. In rank 1, we don't have the congruence subgroup property. It fails very badly. Most lattices are not arithmetic. Most of their subgroups are not congruent subgroups. So there's a recent work by Uri Bader, Zahi Gelander, and Roman Sauer. So I decided to say it because I noticed in Uri's talk it's not in the title, so you're not going to, so then I should mention it because I think it's very relevant. What happens in rank 1? So now suppose that now we have a Farber sequence, but in SOD1. So the rank 1 case in dimension D. So then if D is not 3, then at least you can say that the torsion of the lattice, the torsion of any lattice in the urbanization is at most bounded exponentially by the co-volume of the lattice, where C depends only on D. Just depends on the Lie group. Okay. But the strange thing is that you would expect that this should always be the case, but it's not. In the case D equal 3, this is not true. There's no bound for distortion in terms of the co-volume. So you can have for any function that you choose, you can find a Farber sequence of lattices in SO31. In other words, basically here, which breaks this function. The torsion grows faster than that function in the co-volume. I find this very surprising. Yes, well, that's what I want to say. Thank you.
What makes the difference? What makes the difference between D equals 3 and D greater than 3?
I think Uri can answer, but they use some kind of this method for creating new lattices, Piasecki-Shapiro type construction. Do you know?
No, that will give you the dimension 3 counterexample, but what's the property which enables the proof to work for D greater than 3 and does not work for 3?
I think it's somehow the knowledge of the injectivity radius of these manifolds, and so there's some earlier results by Gelander where he bounds the number of generators of a lattice in terms of C times the co-volume. Yeah.
This works for D equals 3 as well.
Yes, but then for in order to bound the Abelianization, then you also need to bound the length of the relations, and I think there's a difficult. Actually, probably Uri can answer that. Yes.
Maybe I can answer, but I prefer to make another comment about D equals 3. There is a recent work by Nikolay. What's the name? I'm not sure how to pronounce it. Franchi, right? Emmanuel. So he proved the same thing, but for in D equals 3 for arithmetic lattices.
Oh,
So there is a bound for arithmetic lattices.
aha, yes, yes. So if here put arithmetic, then it will be, there's a bound for that sort.
Any other questions, comments?
So, is there any known cocompact lattice in SLN R that's known to be not right angled?
Oh yes, yes. They come from division algebras. If you take n to be prime, then a division algebra of prime degree has this property that any two elements of which the relation of being of commutativity there is a transitive relation, so you cannot escape. So this is a completely this is not going to help in general. This right-angled approach, just it's a nice example, co-compact example, but it's not going to help to deal with the other co-compact lattices.
Any other questions, comments?
You have an example where the rank is 0, but this is non-zero?
Open question that I forgot to mention. Find an example where the torsion growth. Find one finitely presented group with a Farber sequence of finite index subgroups for which the torsion really grows exponentially. Everybody believes there is an example. Conjecturally, here are all these examples. Numerically, they can be, they're really believable because they have been checked for many different primes and so on. So everybody believes it, but nobody can prove it. The problem is it's very hard to get lower bounds on this torsion because it really starts to involve real some number theory because it's about the greatest common divisors of certain determinants. So yeah, very good open question. Fine example of really exponential torsion growth.
Any more questions, comments? Okay, let's thank the speaker again.